So we're trying to find the area under a curve. So you find it by adding up a bunch of rectangles. I'm sure we can find the C. There's got to be a C somewhere. Yeah, there's some back there. I mean, you hate them sitting in the aisles. Also, the fire marshals hit upset. Because if there's a fire, I can get out the back door. You guys are on your own. Seriously, it's nice knowing all of you. I'm just going right away. I'm not sure anything in this room would actually work. I don't want to test that here. So, okay. Jackie, you ready?
Yeah.
Did you start?
Yeah.
Jackie?
Yeah.
You start?
Yeah.
Okay, so you got all of this already?
Just like the last few
I'll
seconds.
edit it out later.
Okay.
It's really not that interesting. But thank goodness I haven't done any swearing yet. Because, you know, I want to keep that out of the recording. Alright, we're trying to find the area underneath the curve. So, let's just do something where it's not with this infinite and delta x and all that stuff. Let's do a straightforward one first. Suppose I want to find the area of the curve x squared plus 5. Not 1 to 3, sorry. Okay? So you go from 1 to 13, and I'm going to use 6 rectangles. First of all, x squared plus 5 is a parabola. It sort of looks like that. It doesn't really matter. And this is x equals 1. And that is x equals 13. Now, we'd love to find exactly what the area is, but that's hard to do. So we're going to just do an approximation. And we're going to say, well, what if I just make a bunch of rectangles underneath, as showed you last time? If I do enough rectangles, I should get pretty close. So, I'm going to cut this into 6 equal-sized rectangles. Of course, they don't have to be equal, but I'm going to make them equal size. And to get the height of the rectangle, I take the interval, and I start on the left side of each interval, and I go up to the curve. And that gets me the height of the rectangles. Like that. Now I know this height is going to be too small. But remember, this curve is sort of blown up. And I'm going to make a good guess. So these are what we call left-hand rectangles. Do that over here. Okay. So how wide is each rectangle? Each rectangle has a width of 2. From 1 to 3, from 3 to 5, from 5 to 7, so they're all 2 wide. So when I'm doing my fancier notation, that's going to be my delta x. That's going to be how wide they are. Okay? So the first rectangle has a width of 2, and has a height defined by evaluating the equation at x equals 1. The next one still has a width of 2, and it has a height by going to f of 3. And I go to 3, I go up the curve, and I go across. And then the next one, I go to f of 5, and so on. Okay? And I could certainly factor 2 out. So I could also say this is 2 times f1, f3, f5, f7, f9, f11. Okay? And then I just have to evaluate f of 1, f of 3, f of 5, which I find by plugging into the equation. Right? F of 1 is 1 squared plus 5, f of 3 is 3 squared plus 5, and so on. So we understand this? This is called the left-hand rectangle. It's called left-hand because I use the left-hand side of each interval. Some folks call it left endpoint. Some just call it left. Okay? And I know I'm going to be underestimating the area of the curve because each of these rectangles, when I draw them, comes under the graph. So far, so good? Now, I'm actually not going to calculate this because I have a life. Okay. Now, what if I want to do right-hand rectangles? Really color here? Maybe not. Now, when I go to 3, I go across, I end up above the curve each time. I go 7, 9, 11, 13. Okay, you all see how that's above the graph? And the piece that's under and the piece that they're above are not exactly equal because the graph is curved. It's not a diagonal. It's not a straight line. But it's close. So if I want to do right-hand point rectangles, right-hand rectangles, I take each of these intervals and I use the right side to calculate the area. So for the right-hand rectangles, each one has a width of 2. And now, I'm going to start at 3, because this first interval is from 1 to 3, so I do the right side, and the next interval is 3 to 5, I do the right side, and so on. Who's confused on that? Feel free to raise your hand. No confusion? Confused, what are you confused? Sure. Each one of these rectangles has an interval, right? 1 to 3, for example. So the left side is f of 1, is x equals 1. And the right side is x equals 3. So if I want to use the left endpoint, I can use f of 1. If I want to use the right endpoint, I can use f of 3. And that gives me the height of the rectangle. Starting at 3, I go where it hits the curve, and then I go across. The next way, I go from 3 to 5. And on the right side, I go up to 5 where it hits the curve, and go across. Okay? So this would be f of 5, f of 7, f of 9, f of 11, and f of 13. Okay? Now I could be fancy. I could say, I'm not going to use the left or the right side. I can use the middle. I can do that. Sorry about that. I'm using 6 rectangles, by the way. Of course, you could use more rectangles. So if I want to use the midpoint, notice what will happen is you get a better understanding if I do a bigger number. So for example, at x equals 10, the left side will overestimate and the right side will underestimate. So they use the midpoint to get up to the curve. Some of it's over and under the curve, and some of it's above the curve. So those two pieces might cancel each other out. So that's another way of estimating the area underneath. So for midpoints, they still have widths of 2, but now use the midpoint of each interval. So f of 2, f of 4, f of 6, f of 8, f of 10, f of 12. Okay? So I can use the left side. The left side I use f of 1. The right side I use f of 3. The midpoint I use f of 2. It makes sense? So each interval, I can start from the left, I can start from the right, I can start from the middle. Okay? And they'll each give you different answers. And this one will be approximately halfway between these two. So on its own, the midpoint is a very nice estimate. Or I can take 1 and 3 and I could average them. If you really want to be fancy, you get trapezoids. Trapezoids give you a very nice, we're going to learn that. It gives you a very nice estimate. Okay? Then there's something called Simpson's rule, which is precise. You get the exact answer. But for now, we just do these. Okay? And of course, we're going to learn how to do them the real way, so all this is going to matter. It's kind of like when you took 1, 2, 125 and you learned the definition of the derivative, and you learned all those shortcuts. You said, why did we do it the other way? You said, now you understand it better. Did you understand it better? No. But we gave it a shot. Okay, so that's how you would do the area with a finite number of rectangles. Now suppose I didn't want to use a finite number. Suppose I wanted to do an infinite number. Or a big number. So imagine that there's lots of rectangles. I'm going from 1, eventually I'm going to end up at 13, but it's going to take a while. Okay? So how wide do I want to be each rectangle? Well, I want to have n rectangles. So the whole interval has a width of 13. So the width of each one will be 12 over n. Okay? You take the endpoints, you subtract, that's how wide the interval is, you divide by n. So if it's going from 1 to 100, it would be 99 divided by n. Does that make sense? Okay. So if this is 1, what's the coordinate, what's the x coordinate there? So I take the 1, and I'm going to add 12 over n. That's that point. I moved 12 over n to the right, and then n could be whatever number I want it to be. So when n was 6, 12 over 6 was 2, and 1 plus 2 was 3. Okay? But if n is 1,000, then the first point would be 1, and the second point would be 1 plus 12 1,000ths. And then the next point would be 1 plus 12 1,000ths plus another 12 1,000ths. Does that make sense? If I have n equals 1,000,000, it would be 1 plus 12 over 1,000,000. Then the next one would be plus another 12 over 1,000,000. Plus another 12 over 1,000,000. Okay? So, in general, points, I'm going to have the first point be 1. Then I'll have 1 plus 12 over n. Then I'll have 1 plus 2 times 12 over n. 1 plus 3 times 12 over n. And so on. And that's going to be the x coordinates of each of those points. And I have to add all of those up. And where do I stop? Well, I started at 1 plus essentially 0, 12 over n. So the last one would be n minus 1, 12 over n. And that's kind of annoying, that n minus 1 thing. So another way I could do this is instead of starting on the left side, I can start on the right side. And then the last one would be 1 plus n 12 over n. So this last point, 1, I've added n, and n rectangles, of course, that just gives me 13. Okay, but you have to do this, we have to use the abstract notation. Okay, so what does that look like? Well, I'm going to have area. Okay, so what did I do? I factored out the width. So the width is b minus a over n. Right? So in this case, 12 minus 1, 13 minus 1 over n. And I've got an f at 1 plus 12 over n. F at 2 plus 12 over n. No, 5. Sorry, ignore that. 1 plus 2 times 12 over n. 1 plus 3 times 12 over n. And the last one is also known as f of 13. Confused? Yeah. I'd be confused if I were you guys. Are you confused? We'll clear it up because we'll do some concrete examples in a minute. Okay? What I'm doing is the same thing I did before. All of these rectangles have the same width. I find the width by taking the whole interval and saying I'm going to have n slices of it. Okay? So I'm going to take the distance from 1 to 13, which is 12, and I'm going to cut it n times. So the width of each rectangle is 12 over n. Then you get the height of each rectangle, I take f, and you're going to start the right end point of each interval. So the first interval is 1, and I move 12 over n to the right. The second one is 1, and I move 2 12 over n's to the right. And I move 3 12 over n's to the right, and I keep going until I move n 12 over n's. Okay? We don't really want to do that, because that's messy. But that's the formula that you want to work with. So now let's put this in math language. That's the fancy way of writing it. Okay? So what do I need? The width of this, whatever curve we've got, this is A, going to B. Oh, these are all very class. Oh! Stop. At least I have friends. Okay, so this whole thing is b minus a and y, and each of these rectangles has a width. And I get the width of each rectangle by taking the whole b minus a and dividing it by n. Okay? So I call that delta x. It's just more compact delta for the difference between the x's. Okay? And then I start at a and I add 1 delta x, 2 delta x, and 3 delta x. I keep going to the n delta x. And of course I could just let n go to infinity if I wanted. So if I want to use the fancy sigma notation, it's good. You guys love sigma notation, right? How many of you don't know sigma? I think I did that last time. A few of you. Okay? But the way they do it in the book is they sort of leave that out. So let's do an example. Let's actually do a problem where we can figure this out. Okay, so we're going to find the area of the curve y equals x squared, x equals x squared, and go from 0 to 1. Nice and simple, right? That's the curve. That 1 is just a parabola. Okay? So I need two things. I need to know how wide is each rectangle. Well, how far is it from 0 to 1? 1. Okay? So delta x equals 1 minus 0 over n, which is just 1 over n. Okay? So how far, now how can I come up with a nice way of writing all the other stuff? Well, let's see. I can start f at 1 over n. I'm going to have f at, really, sorry, f at 0 plus 1 over n, plus f at 0 plus 2 times 1 over n, plus f at 0 plus 3 times 1 over n, okay, all the way up to f at 0 plus n times 1 over n. The width of each of these is 1 over n. That's what we're working with. Now I can simplify that. But wait till he gets his copy. Good. So this is f1 over n, f2 over n, f of 3 over n, f10 over n, also known as 1. Now, if I wanted to use the fancy sigma notation, that would look like this. Big enough? You guys see that? So what does that sigma mean? Sigma means sum. We're going to add things up. I start at I equals 1, and I go up to n. If any of you have done computer science, this is a do loop. Okay? This is the beginning of where you increment, and you step by 1 each time until you get the end of the do loop. Okay? If you don't know computer science, it's the same concept. You're going to start when I equals 1, you're going to add 1 each time until you get to n. You can add them all up, and that's what's going on. Okay? I start with I equals 1, then I equals 2, then I equals 3, all the way up to I equals n, and then I add them all up. Okay? I don't know if we're actually going to test do anything with sigma notation. I'm not sure, because I'm not in charge of the test. Okay? This is what we're looking for. So, for example, on the homework, one of the questions, that's what they're looking for in part 1. Now, there's one more step, of course. What's f of x? F of x is x squared. So we would say that the area equals, I can pull the 1 over n out of that sigma. Why can I take the 1 over n out? Well, it doesn't have any i's in it. So since it doesn't have any i's in it, when I plug in I, it's not affecting this at all. Okay? And what's f of x? F of x is just x squared. So 1 over n squared. Okay? So if I had sine of x, that would be sine of 1 over n. Okay? If I was finding the area under e to the x, that would be e to the 1 over n. If I was going from 0 to 1. Now suppose I want to do an infinite number of things. Well, then I just take the limit. And here's the fun part. How do you evaluate that limit? Anybody have any idea how to evaluate that limit? Well, we'll figure it out. So let's look again at what we've got, right? We've got, I'm just going to rewrite it over here. Okay? That's the same thing as I can just distribute that squared, right? Some of you make better sigmas than I do. Now remember, I said you don't care about this n because I'm only putting in for I. So I can pull out the n squared and make that 1 over n cubed. So I squared. And there's a formula for that last step. What is the sum from 1 to n over I of I squared? 1 squared plus 2 squared plus 3 squared. Okay? That's really what that sigma means. And you may not remember this from high school math. You may never have learned it. I'll write it over here. It's equal to that. It's okay, you weren't supposed to memorize that. You weren't supposed to know that. We would tell you. Okay? So in other words, I can take this and replace it with that. So yeah, 1 over n cubed times n plus 1 1 is 2n plus 1 over 6. You hate your lives yet? Yes, you do? Question. Well, most of the people don't understand either. So where don't you understand?
How does the n after 1 equal to 6?
So how did I replace that? Well, this is a formula that I'm telling you. Okay? If you want to find the sum from I equals 1 to n of I squared, in other words, if you want to add up the sum of squares, the formula is n times n plus 1 times 2n plus 1 over 6. Let's test it. 1 squared plus 2 squared plus 3 squared plus 4 squared should be 4 times 4 plus 1 is 5 times 8 plus 1 is 9 over 6. And I believe that's 30. Yep. 1 plus 4 is 5 plus 9 is 14 plus 16 is 30. It works. So I tested for 1, so I think it works for all of them, right? That's not really math. You can prove this by induction, among other things. So it's a formula that I just give you. But by knowing this, you can now find that limit. So let's cancel it in. Okay. And now I want to do the limit of this thing. Because that's really what I'm trying to figure out. Any idea what that limit is? You should be able to do it in your heads. Multiply out the top. Where should I put it? I guess I can do that. Nope. That becomes the limit. N goes to infinity. 2n squared plus 3n plus 1 over 6n squared. Remember what you do? The n squared is the same. So that's just equal to 2 over 6. Or 1/3. Okay? That horizontal asymptote rule. Remember this? We did this for like a minute back at 125. You don't remember every minute at 125? Really? Sorry. Anyway, okay, so that's how you find it. So, the long answer is the area under the curve, y equals x squared, from 0 to 1, is exactly 1/3. Which we're going to prove in a couple more minutes. Okay? So I am totally lost. I have no idea what I'm doing. Let's do another one of these. Maybe after 2, you'll be a little less lost. Okay? So suppose... I'm going to erase it in a minute. I'll give you guys 1 more minute to write things down. Not for this class, so I want to worry about this. Alright, let's do another one of these. So this is exactly the same as the way you would do problem 22A and B. That's of any help. Now you have 2 options. You can try this on your own first, or we can do it as a team. Who looks a team? Really? There's no I in team. We can keep this all together, right? You know the response when somebody says no I in team. Me. Me is a team. Right? Got an M, got an E. That got me 10 laps when I pointed it out to my coach. Alright. So how do we do this? Well, it's kind of like the other one. I haven't really changed it very much. So let's figure out what I need to do. I need to find B minus A over N. Same as before. If this was from x equals 1 to x equals 5, that would be 4 over n. Okay? If this was from x equals 1 to x equals 10, that would be 9 over n. Okay? So it's just the difference between the x's over n. So I'm going to find, I'm going to start at 1, so I'm going to have f at 1 plus 1 over n. F1 plus 2 times 1 over n. Plus f at 1 plus 3 times 1 over n. Just like before, I start at 1, and then just adding a bunch of 1 over n, which is the width of each of these intervals. So far, so good? Okay. Now, what is f of x? F of x is x squared plus 1. Okay? That's my first one. That's really what I'm doing. Okay? Yes?
Y squared.
The function is f of x equals x squared plus 1.
Alright.
The function is f of x equals x squared plus 1. So I have to take this, and I have to plug it into x squared plus 1. So my first one is 1 plus 1 over n squared plus 1. 1 plus 2 over n squared plus 1. 1 plus 3 over n squared plus 1. Up to 1 plus n over n squared plus 1. That's my function. Yes? It's right hand. We're using right hand rectangles. Yeah. Why do we do right hand? We do left hand. We do midpoint. It's just, there's lots of other math and stuff. If you want it all complete with each other in notation later, using right hand just works better. Okay? I'm amazed. I thought attendance would be dropping out of the video, but I guess not. We'll see. It's very impressive. We'll see how long you guys hang in there before you start class. I need chemistry. When's the first chem exam? 2 weeks. Okay, so we won't see you guys. That's right. Yeah, I usually get about a third of class that day. That's when I give away all the answers to the midterms. Just so that. Oh, and the camera is the whole person that day. All right, so now that's a perfectly good answer. If I want to make this more compact, I put this in sigma form. Room to write it down there? Sure. I'm trying to write very large. I get that. So where I had all those numbers, I now replace them with a letter. So I use I. I can use any letter I wanted. Okay? And I start I at 1, and I go up 10. Can you guys all see that? Is that visible to those people who have to sort of see past that desk? I hope so. I'll write it again. Where can I put it? I guess I'll put it here.
Or is that the one?
Okay? That's what that says. That's the 1. You should stick around just in case I lie. Alright, now, we've come up with a formula. So if I wanted to find the actual area, all I have to do is let n go to infinity. Why does letting n go to infinity work? It's now got an infinite number of rectangles. They're all infinitesimally thin. So there's going to be little strips. When I add them up, I'm going to get exactly the length of that area under that curve. Okay? You saw this with first semester calculus. You're always doing the limit as opposed to infinity. Then you showed me the shortcut, and then you hated us. Shortcut's coming. So let's evaluate this. Now before I evaluate that, you're going to need two very easy formulas. Actually, three. I'll explain why you need this in a minute. Alright, I'll do this a different way. I'll post it later. For those who've been following me so far, it's just been mostly pictures of Bonnie, but we're working on the other stuff. Bonnie will be back soon. Alright, right, Jackie?
Yep.
Bonnie will be back soon.
Yep.
Get excited. Jackie Young is one of Bonnie's owners. Okay, these are going to be very helpful when you want to evaluate that. Okay. So I'm going to do 1 over n times sigma 1 plus I over n squared plus 1. Oh, I turned that light out. That's the way it goes. Alright, let's multiply that out. I get that by FOILing. Yeah, all I do is I multiply this out. FOIL that out. I'm ignoring the limit for now. Okay, so here's stuff you don't yet know about sigmas and things. You can break this up. I could do the first one and then the second one and the third one. So in other words, I could make this 1 over n, I equals 1 n 2 plus 1 over n, I equals 1 to n of 2I over n plus 1 over n, I equals 1 to n of I squared over n squared. Okay? Just sort of distribute that sigma. Yes? That step to this step? This way? Yes, I FOILed this out. I took 1 plus I over n and I multiplied it by 1 plus I over n. So 1 plus I over n times 1 plus I over n. 1 times 1, I over n, I over n, I squared over n squared. Okay? So FOIL. Anyway, alright. So now I've got these 3 different sigmas, so that's where these formulas are going to show up. Okay? Because what does this really mean? This means do the sum from I equals 1 to n of the number 2. In other words, take 2, and then add another 2, and add another 2, and then add another 2, n times. That's what this formula says. You take k, you keep adding it n times, you get n times k. So I'm here, I'm just going to get 1 over n times 2n. Another person. That's the Beatles, by the way. They were a band a very long time ago. Before your time. Alright. Now, I'm going to find this sum. Well, I can pull the 2 over n out. I equals 1 to n of I. So I just took the 2 over n and I pulled it out. And the sum for I equals 1 to n of I is going to be this. I know these are painful. They really are. And it's very easy to get lost because I don't like these either. Why is 2? Well, I have this 2 over n and I pull it out and I get 2 over n squared. So when I say, oh, the sum from I equals 1 to n of 2 is, I'm going to do I equals 1 to n of constant, which is n times constant. Right. Okay? I'm just doing some algebra, folks. Okay? Here I'm going to pull out n squared out and I get 1 over n cubed. So that now becomes, I'll leave that the way it is for a moment, 1 over n times 2n plus 2 over n squared, and then that formula is n times n plus 1 over 2. You should have learned that back when you did series school. You just added up to number 1, 2, 3, 4, up to a number. N times the next number, n plus 1 over 2. And the last one, 1 over n cubed, and this is the formula I showed you a few minutes ago. Okay? If I had a cubic term, I need the bottom formula. But I don't have a cubic term here. However, I might have one on homework problem number 22b. Yes? I can't hear you, Lee. We're finding the area. We just are going to keep going. This is a bunch of algebra. Escrow check. All right. So what did I do, right? What I did was I wrote out an equation for the area, and now I'm really just simplifying it over and over with all this sigma stuff. Okay? Now I got to here, I got rid of the sigma stuff because it said each one of these sigmas I can now replace with one of those 4 formulas. So this is now 2. This one, let's see, 2's cancel, 1 of the n's cancels, and you get n plus 1 over n. And this one, 1 of the n's cancels, and you get n plus 1 times 2n plus 1 for 6. Yes, 6n squared, sorry. Okay? And now I'm just going to take the limit as n goes to infinity. Well, limit as n goes to infinity of this is, well, n plus 1 over n is just 1. The other one we figured out a couple minutes ago is a third. So this equals 3 1/3, or 10/3. So what I'll do later is I'll write all of this up and put it up in my documents for you guys, okay? I also have some stuff in my book. So you may not be aware of this. I wrote the Princeton Review AP Calculus book. Some people know this, but a very small number. So if you don't know my biography, I'm one of the people who helped start the Princeton Review many years ago. It's not Khan Academy, but I had my moments. So we have a couple other cons in the class. I spotted, but they're the other spelling. Just so you know. Anyway, so back when I worked for Princeton Review, I wrote up the AP Calculus book, which we've now sold a zillion copies. Who knows, maybe even used it in high school. So I will take pages from that are relevant to the course, and I'll put them up in Blackboard in the part that says documents for payment, because somehow the documents section got eliminated from Blackboard, but I have to stick it back in. Okay? So I'll put that stuff up there over the next couple of days. I don't do the infinite stuff because that's not on the AP, but I'll write up a couple pages of notes for everybody, okay? This takes a couple of days, so you have to be patient. All the other stuff, however, will be in the finite number of rectangles on the left and the right and all that. So you can practice. Okay? Alright. So, how was that for fun? Yes. Okay, so this is the same as the previous problem. I'm writing for 1/3, right? Here, notice that n plus 1 and an n. So the power here is n to the 1 and n to the 1. It's the same power. Coefficients are 1 of each. So that just becomes 1. And this is just 2. That doesn't change. You get 2 plus 1 plus a third. Okay? And then up to get 3 1/3. Okay? Well, you really don't remember how to do the limits, okay? What happens when n gets really large? Well, these two numbers really approach each other. So they're the same, so you get 1. Another way to think of this is it's n over n plus 1 over n. 1 plus 1 over n. Now what happens with 1 over n when it goes to infinity? That goes to 0. So you just get 1. Okay? Gotta remember your limits. Okay, no, we got plenty of time left. This class goes to 5 minutes. Yeah. I'll stay here forever doing calculus.
For everything in the class, and the only common service
There's more of this. I'll have you practice one of these instead. Save the other stuff for later. Alright? So, let's practice one more of these. Because we love these, right?
What, this guy? You want to visit it?
Huh?
You want to visit
Okay. Find the area under that ratio we're under. That's x squared minus 2. So x equals 3. X equals 5. Let's see how you do. Okay, so you should have that. You should have gotten to that step. Okay? And then your step from there.
Oh, because you want to do 5.
That's what you're going to be trying to evaluate. Okay? Where does that come from? You take the 3 plus 2i over n, and you're sticking it in for x. Alright, let's get a couple more minutes. Boil out 3 plus I times 2 over n to get that. You just have to FOIL. 3 plus 2i over n times 3 plus 2i over n. I know this is hard. As I said, this is the most difficult abstract stuff we do. You've never really done this before. Why is I equal 1? Well, I is a counting. This is a counter. Okay? It helps me keep track of how many 2 over n's I use. So each time I go from 3, and I move 2 over n to the right each time. Okay? So I start once, and then I just keep going. So that's why I have 1, 2 over n, 2, 2 over n, 3, 2 over n, etc. Yes? Well, as I said, I have 2 over n, and move 2 over n again, and move 2 over n again. So I have I times 2 over n, which is just 2I over n. Okay? I have I of these, 2 over n. So I start with I equals 1, and I just keep adding 1 to it each time. If you think about the number line, this is 0.3, and I move 2 over n to the right, and I move 2 over n to the right again. So I did it 2 times. And I move 2 over n to the right again 3 times. Okay? Each time, if I prolong the number line, I'm moving 2 over n to the right. So this I helps me keep track of how many times I do that. Yes? 5 is 2 over n. 5 minus 3 is 2. Okay, and then divide that to n intervals. Okay? So now I get to here. I want to simplify that. Okay? Let's simplify it some more. Remember this just comes from FOILing out 3 plus 2I over n. Okay? Subtracting 2. So I can make that into 3 different sigmas. Okay, so now I can break that up, yes?
How did you get 7?
How did I get 7? I have 9 plus 12I over n plus 4I squared over n squared minus 2. 9 minus 2 is 7. Okay? As I keep saying, I know this is hard. Don't think I'm not sympathetic. I didn't test it last semester, but we're covering it, so I have to teach it. Okay, this is 2 over n. Now I can use my formula. This is just a constant, 7. So when I multiply that out, I get the constant times n, so that's 7n. Next one, I have 12 over n. And the sum from I equals 1 to n of I is just n plus 1, 2. Third one, four over n squared times n plus 1, 2n plus 1, 6. So that's 14 plus did I lose an n somewhere? That can't be right. I lost an n. I got 2 over n. Sorry. Sorry about that. I forgot to distribute the 2 over n. That's a mistake you will make on an exam. Okay, so simplify a bit. And now if we take the limit as n goes to infinity, I'm going to get 14 plus 12 plus, well, 8 times a third. Okay? And then I'll write up some stuff about this. Yes? Well, because this number is a third.
No, is that 24 over n squared on the top? Or is that just 24 over n?
I hope I never see this again.
No,
I'll
in the
write up
middle.
some notes for everybody.
24 over n squared is 24 over n.
Jackie, you can